Hi everyone, this is Dr. Kekan, an Associate Professor, Department of Physics, R.M.K College of Engineering and Technology. In this lecture video, I am going to talk about Faraday's law for electromagnetic induction. So the main topic is here Faraday's law, displacement current and conduction current. Now, according to the Faraday's law for electromagnetic induction, a static magnetic field produces no current flow, but a time-varying field produces an induced voltage is called electromotive force is called EMF in a closed circuit which causes the flow of current. An electromotive force is merely a voltage that arises from conductors moving in a magnetic field or from changing in a magnetic field. So the statement of Faraday's law for electromagnetic induction is the induced EMF in any closed path or circuit is equal to the time rate of change of magnetic flux linkage by the circuit. So this is called as Faraday's law and it is expressed as V the suffix EMF equal to d pi by delta volt or V EMF equal to minus n d pi by dt volts, where n represents number of turns of a supplementary conductor forming the closed path and pi is the total flux passing through each turn. The minus sign indicates that the induced EMF is in such a direction as to produce a current whose flux is added to the original flux so that it would reduce the magnetic uh, field, that is magnitude of the EMF. So this is known as a Lenz law. In other words, the induced voltage acts in such a way as to oppose the flow of flux. So non-zero value of d pi by dt may result from any of the following situations. So one is the time changing flux linking with a stationary closed path, and the second one a time varying loop, that is moving conductor in a static magnetic field, and a time varying loop in a time varying magnetic field. So the transformer EMF, or we can say that the transformer electromagnetic EMF, where the loop is stationary in a time-varying magnetic field. So stationary closed path or conducting loop in a time-varying magnetic field B is shown in the figure. So here, this EMF induced by the time-varying magnetic field in a stationary loop is often referred to the transformer EMF in a power analysis, since it is due to transformer action. So electromotive force is measured in a voltage and it is a form of scalar. It is represented as a line integral of the electric field around a closed path. Therefore, the total flux through a closed circuit is equal to the integral of the normal component of the magnetic flux density B over a closed surface by using Gauss law. So that pi equal to closed surface integral of B dot ds. According to Faraday's law, V EMF is equal to minus d pi by dt. So you can substitute this here, then we can get R V EMF, that is voltage EMF is equal to line integral of V dot dl is equal to minus d pi by dt. So that the by using the equation 3.3 in equation 3.5, so we can get the V EMF equal to line integral of V dot dl is equal to minus d by dt of surface integral B dot ds, where V EMF is called transformer EMF. If the circuit is stationary and the field is moving with the time, then the above equation can be rewritten as minus surface integral dou v by dou t into ds. The above equation is called Maxwell's second equation in integral form. So it states that the electromotive force around a closed path is equal to the negative of the integral of the time rate of change of magnetic flux density over the surface bounded by the closed path. Therefore, by applying the Stokes theorem, the left hand side of the above equation is equal to it is a closed surface and closed surface integral del cross E ds is equal to minus dou v by dou t of ds surface integral. So that by using Stokes theorem, so Stokes theorem deals with the line integral into surface integral, so that the above two integral to be equal, their in the integral must also be equal. So therefore, del cross E equal to minus dou v by dou t. So this equation is the point form or differential form of Maxwell's second equation. So in time varying situation, the equation proves that the both electric and magnetic fields are present and are interrelated. They also imply that the work done in a moving charge about a closed path in a time varying electric field is due to the energy from time varying magnetic field. Then second one is emotional electromagnetic force or moving loop in a static magnetic field. So here the loop is moving and the field is stationary. So that by using Faraday's law F equal to Q of V cross B, V vector cross B, so that F by Q equal to V cross B. We can write F by Q in terms of electric field intensity, that is EM. So EM equal to V cross B is therefore the motional EMF produced by the moving conductor. It is EMF equal to the line integral of EM dl, which is equal to the total line integral of V cross B into dl. The other name of the motional EMF is a flux cutting EMF because it is due to the movement action. So it is the kind of EMF found that in electrical machines such as motor, generator and alternators. So consider a rod to be moving with velocity v between a pair of rails as on the figure. Since the velocity v and the magnetic field is b are mutually perpendicular, then the Vrms is equal to integral of Vb into dx, that is equal to minus Vbd, where d is a length of the conductor or rod. By using applying the Stokes theorem, here we can interrelate the surface integral. So del cross Em ds equal to del cross of V cross B ds. So otherwise we can write del cross Em is equal to del cross of V cross B vector. Then moving loop in a time-varying magnetic field we can given by the general form. So both the transform EMF and the motion EMF are present in this moving loop with a time-varying magnetic field. So that we EMF equal to line integral E dot dl, which is equal to the sum of dou V by dou t ds and V cross B dl. Then applying the Stokes theorem, then finally we are going to get a del cross E equal to minus dou V by dou t plus del cross of V cross B. And we'll solve some problem. So problem here it is, first one find the permeability of the material whose magnetic property is 49. So we know that the relative permeability equation is mu r equal to 1 plus Im, where Im is equal to susceptibility. So that which is equal to 1 plus 49 is equal to 50. As we know mu equal to mu naught into mu r. So mu naught value is 4 pi into 10 power minus 7 into mu r is 50. So that's 6.28 into 10 power minus 5. That is the permeability. Then second one, the magnetic circuit comprising a toroid of 500 turns with the cross-sectional area of 600 centimeter square and the mean radius is 15 centimeter, carries a current of 4 amps. Find the total ampere turns and the reluctance of the magnetic circuit and the total flux enclosed. So the first one is ampere turn, N into I. So N is given 500 into 4. So reluctance is equal to F by pi n pi by I. So n is given, I also is given. So that it is 125 into 10 power 6, 1.6 into 10 power minus 5. Then third question is the ferrite material has a mu r equal to 50, applied to the sufficiently low flux density and B equal to 0.05. So find the magnetic field intensity. We know that H equal to B by mu. So B value is given, mu naught into mu r, it is actually the value. The last one, find the magnetization in magnetic material if mu equal to 1.8 into 10 power minus 6 Henry per meter and H is given 120 amps. So that you can substitute the value mu equal to mu naught into mu r. So mu r equal to mu by mu naught. So mu value is given, mu naught is the constant 4.10 power minus 1, so that you are going to get 1.43 1.4324. So that the magnetization is mu r minus 1 into h. So mu r is given, that is 1.4324 minus 120. Thank you.